All right, so in your books, you're on page 119. Right, we're going to be using the table on page 119. And again, our goal right now is to be able to understand and also calculate the decimal number that appears in every element box on the periodic table. So right now, when we look at the element box, there's two numbers there. One is the whole number, which represents the number of protons, the atomic number, right? And the other is the average atomic mass. Okay? And that's what we're going to calculate right now, is the average atomic mass. So we're going to do that for the element carbon, right? And the nice thing about this is that the answer is right on the periodic table. Right? So we already know what the answer is going to be. Because the atomic mass of carbon is 12.01. Okay, so this is an example of how we can calculate the average atomic mass. For an element, and in this case we're going to calculate the average atomic mass of carbon. Right? And again, looking at your periodic table, we know the answer will be 12.01 AMUs. Now, I don't think we've talked about that unit yet. AMUs? Does that sound familiar? Okay, so real quickly, we don't need to worry about it too much. It stands for atomic mass unit. All right, atomic mass unit. It's a unit that we use for atoms and small particles instead of using grams. Because as we saw the other day, right, talking about the mass in grams of an atom, it's so incredibly small, right? So this is another unit that's used, AMUs, atomic mass unit. All right, calculate the average of atomic mass. Yesterday we wrote down 3 things that we need to calculate average atomic mass. We're going to put them up here again. First is you need to know the number of stable isotopes. Alright, and this is information that we'll get directly from the table. Second of all, we will need to know the mass of each of those isotopes. And third, we will need to know what we call the percent abundance, right, of each isotope. Okay, so let's get familiar with the table that we're using. It's on page 119, right? So, Chrissy, can you just tell us what the title of this table is?
Natural percent abundance of stable isotopes of some elements.
Beautiful. Natural percent abundance of stable isotopes of some elements. What the heck does that mean? Right, so starting with the last thing, some elements. So as you look down the first column, what do you see? You see the names of various elements, such as hydrogen, helium, carbon, nitrogen, and so on. Right, so those are the some elements. And what's the information that we have on some of those elements? Well, they're giving us the natural percent abundance. Right? So this is just fancy word for how much. Right? Abundance asks how much. Natural just means that it occurs naturally. Okay? So it's how much stuff we have of the stable isotopes. All right? Stable isotopes, because some isotopes actually decay. They go away. They're radioactive. So in order to be considered, it has to be a stable isotope. All right, so let's look at this. The first element on there, what is that, Noah? First element on there.
Hydrogen.
Hydrogen, right? All right, so now, that's the first step. So we know we're dealing with hydrogen. The second thing is we want to know how many isotopes do we have. So when you look in the next column under symbol, right? Liam, how many symbols do you see there for hydrogen?
1.
All right, tell me what it is.
H1.
H1. All right, so that's one of the isotopes of hydrogen. Right underneath it, you see... H2 and H3, right? So we have a total of 3 symbols for hydrogen, or 3 isotopes. That's how that's going to work. Does that make sense? Right? So how many isotopes do you see for helium?
2.
2, right? Then carbon we have
2.
2. All right, is this making sense? Because you want to be able to use this table on your own as well. All right, so we said we're doing carbon, right? So the first question is the number of stable isotopes, number of stable isotopes. And we can see from our table that we have 2 of them, right? And I think we used this as an example yesterday. We know that we have C12, right? And the other one is C13. Great? So we have the first step. We have the number of isotopes. The second thing is we want to know the mass of each of these. So as we go across the table, right, we can find the mass. It's the 4th column over. Right, so Devin, what's the mass of the C12 that you see there?
Just 12.
Just 12, right, good. 12, and there are some decimal points, right? 12.000, I think, right? 3 of them?
3 zeros.
Okay, and let's add in the unit, right? We just learned it just a minute ago, but it's no big deal. We're just going to use AMUs, right? Atomic mass units. All right, and then we can see that the mass for carbon 13 is 13.003. Yeah? Cool. So we have 2 pieces of information that we need. We know the number of isotopes, bless you, 2, and we know the mass of each. Yeah? All right, so this final thing, percent abundant, how much of each isotope do we have? All right, Will, can you help us with that? How much? What's the percent abundance of C12? Looking at this table.
Percent abundance of C12.
Yes.
It's 98.89.
Beautiful. 98.89%.
No.
Again, whenever you're doing a problem, calculating average atomic mass, this type of information needs to be available to you, either in your table from a book or maybe it's given to you as part of the problem. Okay? So you just need to get comfortable with seeing it and using it. All right, so the percent of C13 can't be very high then. When we look at the table, it's 1.11%. Cool? All right, let's relate this to the birthday party problem. Right? But instead of ages of kids, we're now dealing with isotopes. So you can see we have 2 groups, just like in the birthday party problem, right? 2 ages, 2 groups. Instead of ages, we now have masses, so we have 12 and 13 there. Right? And we have much more of the C12 than the C13. So right away, without doing a calculation, what can you tell me about the average mass of carbon? It should be much closer to 12 than 13. Right? And that's because there's so much of 12. Right? So it's going to skew that average from being halfway in between 12 and 13 to being very close to 12. And of course, we already know the answer. It's 12.01, and it's very close to 12. Right? So that makes a lot of sense. Yeah? Okay, so here's the calculation. To actually get the number, the average atomic mass, we need to take each isotope. So we'll start with C12. And we take the mass of C12, which is 12.000 AMUs. Don't forget about that unit. And we need to multiply by how much we have. So this is a little bit different from the birthday party problem because in the birthday party problem we use the number of kids, right? Maybe even set it up as a fraction. Here we are dealing with a percent, right? But it's all the same information. It's how many you have, what the part of the whole is, right? So we have 98.89%. So we need to multiply our mass by that. So you remember from math class, when you're multiplying by a percent, you first need to take this decimal point and do what?
Move it over.
Move it over 2 places. Right? So the decimal that we'll multiply by is actually 0.9889. Yeah? Okay, this is the weighted average. We're taking how much we have times its mass. So that's the first isotope. And then we're going to add to that the second isotope, C13. And we'll do the same thing for it. We take its mass, 13.003 AMUs. And again, we need to take into account how much we have. So we're multiplying by its percent, 1.11. Be careful here, this is a common mistake that people make all the time, right? People new to this problem, people old to this problem, make this mistake all the time. You have to move this decimal point not one, but twice, right? So you're adding in a decimal place, a 0. So make sure you do that. It's 0.0111. The error is that people often leave this 0 and they just put in 0.1, right? They forget to move it over 2 places. Okay, so that's how it's set up. Now all that's left is to calculate. Maybe you guys can help me calculate this. One person can take the 12.000 and multiply it by 0.9889. And maybe a second person can do the 13.003 times the 0.0111. Right?
The 0.9889 times 12 is 11.8668.
1.8668 AMUs. Do I have that right? Yeah? Okay, and this makes sense to you, right? Because you're taking 98% of 12, so it should be a number very close to 12, right? 11.8 is close to 12. Are we good with that? Did I write? Yeah? Okay. And do you have the other one now?
0.1443.
3 AMUs. Like that? And this makes sense that it would be a very small decimal, right? Because we're only taking 1% of 13. So that all seems to make sense. All that's left is to add those two numbers together. If we do that, we get, hope you guys can see down here, 12.001.
0.01.
Yeah.
Yeah, there wouldn't be 2 zeros.
12.01. And maybe you get another one. Let's double check. 12.01. Is that able to get that down there?
It's 12.0111.
111. Okay. If we round this to 2 decimal places, which we typically do with average atomic masses, this is the same exact thing. 12.01 AMUs, right? Which is exactly what we expected to get from the periodic table. 12.01.